Gonna breeze right through. More logistics, okay? So with respect to these electrochemical cells that we've been drawing, it's really kind of tedious to sit out and draw all of these various electrochemical cells, right? You have your little half reactions, your little metal electrodes, etc., right? So we have a shorthand method of essentially trying to depict these overall electrochemical cells, and it follows the following convention. So we start on the left-hand side with the oxidation half reaction, right? So this is going to be our oxidation half reaction or our anode cell. And then it moves as we go from left to right to the reduction half reaction or the cathode, what is taking place at the cathode, okay? And it follows the general convention of the oxidation electrode followed by electrolyte, and then the reduction electrolyte followed by electrode. Anytime we change phase, we depict that via just a single line, right? So what do I mean by change phase? As we go from zinc solid, which is our anode, what do we do when we go into zinc 2+? What have we done? We had a solid, now what phase are we in? Aqueous, right? That's a change of phase. That's what you're going to utilize to denote that there's a change of phase. You use a single solid line. Anytime there's a salt bridge connecting the two separate half reactions, we use this little double line instead. Okay, so again, the anode, the electrolyte, we separate it by a single line. Salt bridge with the two lines, the cathode electrolyte, and then the cathode itself. And again, that's going to tell you essentially what's happening in the overall voltaic cell. Okay, so that's great, neat. Moving on. Now, typically, with respect to redox reaction, the anode, the electrode at which oxidation occurs, tends to be the metal that is actually oxidized, right? Whereas the cathode, which is the electrode at which reduction occurs, it tends to be the metal that is actually reduced. Sometimes, though, that's not the case. We can see redox reactions and electrochemical cells that utilize reactions that don't actually include a metal at all, right? So for example, if we utilized this redox reaction where we have iron being oxidized to iron 2+, and then manganese, this is manganese in the +6 oxidation state going to manganese 2+, we have the oxidation, right? The oxidation, we have our nice little anode in the form of iron solid, but where's the metal for the reduction half reaction? In the reduction half reaction, we've got this permanganate, 5 electrons, some protons going to Mn2+, and 4 wires. So where is the overall metal for this guy? There is none, right? But we can still utilize this in a nice voltaic cell. The only thing that we have to do is we have to include something called an inert electrode, okay? What we mean by inert electrode is essentially a metal conductive surface that is just a vehicle by which electrons can enter and leave whatever electrode cell, whatever half reaction they're dealing with. What we mean by inert is the fact that this is not going to actually react overall, right? So this, whatever this metal is, whatever this conductive surface is, doesn't undergo any type of reaction. It's just a vehicle by which electrons can enter and leave the cell. So this metal, this inert electrode, tends to be platinum. Platinum is a nice metal that does not participate in many redox processes. It instead can just be nice and conductive. It can transfer electrons, it can take them, whatever it needs to do, okay? So in that overall voltaic cell that I presented in the first slide, or that last slide previous, we had the iron as our oxidation half reaction, as our anode, but for our cathode, where we see MnO4 being reduced, that's going to be depicted by our platinum metal, because again, it's serving the purpose of just getting electrons into and out of the cell. So now, one little extra thing to note, if you do use an inert electrode like platinum in a reaction like this, then the only other thing that you have to change with respect to our little shorthand notation is the fact that, number one, platinum is the cathode electrode, the actual electrode that's participating in the reduction reaction, but now, for this reduction reaction, we had a bunch of stuff in solution, such as our MnO4, our Mn2+, our H+, all of those are in the same phase, right? So we can't separate those via single lines. Instead, we will separate them via commas. So anything where you have a redox reaction and you have things that are participating that are in the same phase, you just separate them via commas as opposed to the solid line when we actually change phase overall. Okay, so that's just a little note. Make sure whenever you're dealing with our little shorthand notation that you utilize those following conventions. So a couple more things before we finish tonight. We're going to go back to this idea of cell potential. Okay, so I had introduced the idea behind cell potential when we had depicted our original voltaic cell, right? So we had our two half reactions, and we measured the cell potential via our nice little voltmeter, okay? Cell potential, just as a reminder, is the measure of a potential difference between two separate half reactions, okay? It's important to note that there is not an absolute electrode potential, right? If we isolated one of the half reactions by itself, it wouldn't have a potential. It doesn't exist. It has to be in conjunction with another cell so you actually get a difference in potential between the two, okay? It would be nice, though, if we did have some sort of just singular electrode potential for all of our various half reactions. Okay, so building that a little further, what we do is what we do usually with respect to any time we have to measure a difference in something, right? So for example, enthalpy. Enthalpy, we measure differences in enthalpy. There is no absolute enthalpy. But what do we do to kind of get around that so that we can utilize nice little tables and charts of things to calculate the enthalpy for any reaction? We define a zero enthalpy, right? What was the enthalpy that was zero for anyone? Enthalpy of formation? Anything in its elemental state, right? That was relative. We do the same exact thing here. We define, essentially, a zero with respect to reduction potential, and then we measure everything relative to that so that we can generate these nice little tabulated lists of reduction potentials and electrode potentials, okay? Now, what is our zero and standard reduction potential? It is what we call the standard hydrogen electrode. It is an electrode at which the following reaction is essentially occurring. We are seeing the reduction of protons to hydrogen gas, right? This is occurring at a platinum electrode, so our nice little inert electrode is here, and is also occurring at standard state. So what is standard state with respect to anything in solution? We have something in solution. What's the concentration of it if you're at standard state? 1 molar, right? So this means that we have 1 molar protons. What about if you're a gas? What is the standard state of a gas? 1 atm pressure, okay? So we define this reaction where we have 1 mole of protons being reduced and there's bubbling in 1 atmosphere of hydrogen gas. This is all occurring at a platinum electrode. We define this as our zero potential, our 0 volts, okay? So this is the definition of our standard reduction potential. We use this nice little standard hydrogen electrode, or SHE. Okay, so now, if we take our little standard hydrogen electrode, we've made it, we've put it in our lab, and we go in and we connect it to another half reaction, right? So let's say that we connect it to our zinc electrode, where we had zinc solid in solution with zinc 2+. We connect the two together, right, and we measure the voltage. We measure the potential difference between the two, okay? So again, this potential difference, this E cell, is the difference in potential between the final half cell and the initial half cell. And what we're dealing with respect to final initial is in terms of the electron, okay? So we have our anode as our zinc, and our cathode is our SHE, our standard hydrogen electrode. Where does the electron end up? Does it end up on the cathode, or does it end up on the anode? It ends up on the cathode, right? So if we're measuring the cell potential, our final state, this is E final minus E initial, our final state is the potential of the cathode, right? Our initial state, where it started, was the anode. So the cell potential is defined as the potential, or the standard reduction potential of the cathode minus the standard reduction potential of the anode, okay? If we did that, we connected them, which is what we've done, and we found that our cell potential was this 0.76 volts. That's what this is, right? So this is, we've connected them, overall cell potential is 0.76 volts. Do we know, or have we defined one of these with respect to our standard reduction potentials? We've told you, or at least we've ideally told you, that this SHE, what have we defined it as? What is its reduction potential? 0, right? This, in this cell, is our cathode. So this is 0. Can we measure the potential difference, or our reduction potential for the anode from this data? We've defined hydrogen as 0. We've measured the difference in potential between a hydrogen electrode and a zinc electrode, and we've gotten an overall difference in potential of 0.76. With that, we can calculate the reduction potential for the zinc couple, which ends up being a minus 0.76 volts. Okay? So the whole idea behind this, again, is that we want reduction potentials, or kind of like a measure of the tendency to reduce things or be oxidized by things, in terms of just single half reactions. We can't do that, though. We have to have differences. So because of that, or to get around that, what we have done is connected any and all possible redox reactions to this standard hydrogen electrode. We've measured the potential difference between the two, and then we've calculated the other thing from that. Okay? With that, overall, we get these nice, beautiful tables. All of these various reduction potentials, given that they have all been connected and measured relative to our 0 potential, which is our standard hydrogen electrode. Okay? So a couple of things to note with respect to this overall table, right? Up top, we have positive values. These are all positive reduction potentials or electrode potentials. Down below, we have negative values, right? What we see with respect to the arrangement of this table as is everything down here loves to be oxidized. Everything with a negative reduction potential loves to be oxidized, whereas everything up here loves to be reduced. So the more positive the reduction potential, the greater the tendency for reduction. Okay? So with respect to being oxidized, we've also defined that in a different term. If you're oxidized, what are you really good at doing? If you like to give up your electrons, you're very good at giving them to people or other things. So what does that do? If you're giving your electrons to somebody, what do we call you? We call you a reducing agent, right? So these guys love to be oxidized. They are very, very, very good reducing agents. Whereas the things that love to be reduced, what are they good at being the agent of? They're very good at being the agent of oxidation. So up here, anything with a very positive reduction potential, it's a very strong oxidizing agent, whereas things with negative reduction potentials are very strong reducing agents. And so now we have this great tabulated list of standard reduction potentials. We can calculate the overall cell potential for anything we would ever want to calculate, given that it's on this table, at least. Okay? And we will have to wait on that until next time. So again, and then we can utilize that to calculate the cell potential for anything we could possibly want, given the redox reaction. Okay? So what was that standard, or that arbitrary 0 that we defined? What was the reaction? So our arbitrary 0 was the hydrogen electrode, right? The standard hydrogen electrode. And it was essentially just the reduction of protons to hydrogen gas, right? So we said this reaction is going to have a 0 volts, and we are going to measure everything relative to it, okay? So utilizing that and the fact that when we calculate these cell potentials, we're essentially taking the potential of the cathode and subtracting from it the potential of the anode, we have been able to tabulate all of the various possible half reactions that you could ever want to look at, okay? And so that is what is given in our nice little standard tables just like this, okay? So now, there's a couple of things, because we're going to be dealing with these quite a bit, so I want to introduce you to it. A couple of things to note about this little standard tabulated table, okay? These things, these actual potentials, right, are measured in volts, okay? And right now, these are all at standard state. So every time they give you a table like this, all of the reactants and products are at standard state. Again, all of these potentials are measured relative to the standard hydrogen electrode, which has this 0 volt potential, okay? Now, another thing to note about all of these guys is that they are all written as reductions, right? So this is why I tend to call these guys standard reduction potentials, because the way they're written in our little table is as reductions, even though sometimes we'll need to utilize them as oxidations, okay? So all of these guys are written as reductions. I also noted last time that everything up here with positive potentials, positive standard reduction potentials, all of these guys love to be reduced, okay? So everything that had a positive value with respect to the reduction potential relative to hydrogen loves to be reduced, whereas everything down here at the bottom of the table that had negative potentials, these guys all love to be oxidized. They love to give up their electrons, okay? So if you love to be oxidized, you're very good at being oxidized, what does that make you very good at being? So things that love to be oxidized are very strong reducing agents, right? Because if you're oxidized, you've given up your electrons, you've reduced somebody in the process, whereas things that love to be reduced are very strong oxidizing agents, okay? So given a nice list of these reduction potentials, you should be able to determine who's the stronger oxidizing agent or who is the stronger reducing agent just based off of these values, okay? Okay, so that's great. That's kind of the build. Now we're going to move on, get something different done. So again, just as a reminder, by convention, these potentials are always written as reductions, okay? So again, we'll talk about this when we utilize it, but because these potentials are written as reductions, it's going to maybe kind of confuse you just a little bit. And that's the only reason why I mentioned this, okay? Okay, so let's go ahead and try a problem utilizing these tabulated standard reduction potentials or electrode potentials, right? So let's say we have a reaction where we have aluminum reacting with nitrate and some protons going to make aluminum 3, NO, and water, okay? This is a redox reaction. And it has the potential, again, to generate electrical energy if we made a nice little voltaic cell that utilized the two half reactions that were present in this overall redox reaction. So what we're going to do now is we're going to calculate the cell potential that could be generated utilizing this redox reaction, okay? So the first step in doing this is, again, figuring out who has been oxidized and who has been reduced. So how am I going to determine who has been oxidized and who has been reduced? To determine who's the cathode and who's the anode in this overall redox process. I'm going to assign oxidation states, right? So I worry that we're not very strong in assigning oxidation states because that is going to, like, pretty much everything is built off of your ability to determine who is oxidized and who is reduced, okay? So if you feel like that is a weakness of yours, maybe you should come see me after class or something like that. Email me over the weekend, okay? All right, so if we go ahead and start with aluminum, what is the oxidation state of aluminum? 0, right? This is aluminum in its elemental form. First off, let's just instead of moving on to nitrate, let's go ahead and move immediately to the products, which is aluminum 3. What's happened to aluminum? What is the oxidation state over here in the products? +3, right? So immediately you can see what's happened in this reaction with respect to aluminum. It's been oxidized, right? It's lost how many electrons? And that's going to be an important thing. It's lost 3 electrons, right? So this guy has been oxidized. And specifically, it's lost 3 electrons, okay? So I'm going to go ahead and write out the oxidation half reaction. Okay, so this oxidation half reaction, we're going to write aluminum solid going to make aluminum 3 plus 3 electrons. Okay, and remember in oxidation half reactions, electrons are products. Okay, all right, so next let's figure out who's been reduced. So I'm going to go ahead and sign the easy ones. So proton +1, that's fairly simple, right? If we go back to our nitrate, between nitrogen and oxygen, Oxygen is more predictable. There are 3 of them, and oxygen tends to have a -2 oxidation state. So nitrogen is going to be whatever it needs to be for this guy to sum to the overall charge of the molecule, which is -1. So what is the oxidation state here of nitrogen? +5, right? So we'll put a +5, X is equal to, I've signed all of the reactants. Now if we move over to the products, NO, we've got a -2 for oxygen. Again, what does nitrogen have to be if it's going to sum to 0? +2. And then for water, we would have a -1, and then a 2 times a +1 equals 0. So a +1 and a -2. So who gets reduced here? Nitrogen, right? So nitrogen goes from a +5 to a +2, right? So specifically, how many electrons does nitrogen gain? Goes from a +5 to a +2. We have gained 3 electrons. So that is reduction, right? I'm going to write out the reduction half reaction. So reduction. And now for the reduction half reaction, everything's going to come with it, right? All of that leftover stuff. So we've got NO3 minus plus 4 protons plus how many electrons? 3 goes to make NO plus 2 H2O. Okay, so what do you think the hydrogen and the waters and all of that is there? Thinking about what we talked about at the beginning of class on Tuesday, why would we need to include oxygens, or why would we need to include waters or protons or anything like that? To balance with respect to mass, right? These half reactions, they're all balanced with respect to mass, and so that's where all of this extra stuff is coming from. But this is the specific half reaction that you guys are going to have to look for. Okay, so now we have written out our 2 half reactions. Now our job is to go into that table and find these particular half reactions, okay? So for the reduction one, you will find, listed in that table, nitrate plus 4 protons plus 3 electrons going to make NO and 2 waters. And you look it up, you'll find it. That half reaction has a potential of a positive 0.96 volts, okay? Then you will go in and you will look for aluminum, going to make aluminum 3 plus 3 electrons. But that would be wrong. Why would that be wrong? What are you going to find in the table? You're not going to find oxidations. You're going to find reductions, right? So if this is our oxidation half reaction, what should we be looking for in the table? Not the forward, but which direction with respect to this reaction? The reverse, right? So you should be looking for aluminum plus 3 electrons going to make aluminum solid. When you do that and you find that potential, you'll find there has a potential of a minus 1.66 volts, okay? Even though when we look and when we utilize this, it's reversed, we're not going to change the sign. We're taking it as is, specifically as written in the table, okay? Okay, so now we're at the end. The purpose of this was to calculate the cell potential. So now all we need to do is we need to take the reduction potential of the cathode and subtract the reduction potential of the anode. Again, what happens at the cathode? What particular process? Which half reaction occurs at the cathode? The reduction process. So you could also look at this as the reduction potential of the reduced one minus the reduction potential of the oxidized half reaction. So this ends up being, who's reduced here? The nitrate, right? So we have a positive 0.96 volts minus whoever is oxidized, which is the aluminum, a minus 1.66 volts. This is our cell potential. So when we add those two together, we get a positive 2.62 volts. Now again, the only thing I want to note, there's going to be a tendency to want to flip the sign of this, because again, we don't use it as a reduction, even though it's written as a reduction in the table. Do not do that, right? You just write out your half reactions, you find their potentials listed as reductions, but you still use them as is. So however they're written in the table, it's the cathode minus the anode, go with it, that is your overall cell potential for this redox process, right? So this could generate 2.6 volts of potential, which is great. Be used to man a battery or something like that. Okay, so that is an example. Let's go ahead and do a problem to get that into your head a little bit better, right? So I have a redox process. I want you to calculate, again, the cell potential using our standard tabulated electrode potentials, reduction potentials. can't zoom in on your, no, it doesn't work like that? Okay, so go ahead and get your answers in. We'll go over this one. Okay, so let's go ahead and talk about this one so that we have enough time to get through everything. So we've got lead reacting with chromium metal, making lead metal, chromium 3+. So who's being oxidized here? Who is the oxidation half reaction? We've got chromium, so we've got chromium solid going to chromium 3+ ions. How many electrons is it losing? 3, right? It goes from a 0 oxidation state to a +3, so it loses 3 electrons. That's important. There are multiple different oxidation states for chromium. They all have different potentials. So make sure you're noting that this is the couple that has chromium going to chromium 3+. For the reduction, who are we reducing? Lead. How many electrons is it gaining? 2. So 2 electrons going to Pb, solid. So we go to our nice little handy reduction potential table, and hopefully you can read it. Oh, I've lost mine. So for the chromium half reaction, we get a reduction potential of a minus 0.73 volts. And then for the lead half reaction, we get a potential of a minus 1.13 volts. So now, if we're going to calculate the cell potential, we're going to take the cathode half reaction, subtract the anode half reaction. So who is the cathode here? Cathode is reduction, so it's the lead reduction potential. This is 1.3 volts minus a minus 0.73 volts. Again, do not be tempted to reverse anything. So when you do that, minus a minus is a plus, and overall you end up with a 0.60 volts. Are there any questions about that? Okay, most of you got this correct. It was just not putting it into Socrative the way I was requesting it. Okay, so that is it.